spent a lot of time talking about limits. We've talked about a limit at a point, we've talked about a one-sided limit, and now we want to talk about another concept of limit, and that's a limit at infinity. So what does that mean? Well, in many situations, we are interested sort of in the long-term behavior of a function. So for instance, if we're looking at a function describing the population of some species at time t, then we would like to know, well, how will this population behave as t goes to infinity? Right? So if this function describing the population goes to 0, well, that means the species becomes extinct. Right? Now, depending on what you're talking about, you wouldn't like this to happen. Right? So, let's see. How do we describe this concept of a limit at infinity? Well, if we say that the limit of f of x as x tends to infinity is L, right? Intuitively what we mean by that is that we can get f of x as close to L as we like just by taking x large enough. Right? So, thinking about the definition of a limit at a point, you may want to say that something like this. And we have to be very careful here. Right? This infinity, right, it is not a number that we can add or multiply or subtract using another number. Right? So this expression, x minus infinity, doesn't even make sense. Right? So we can't talk about x getting close to infinity. Right? Because infinity isn't a number, So instead, we have to write this down in a different way. Right? So, let's see. If we look at the graph I've drawn here, right? And so we want f to be close to L, right? So just as for other kinds of limits, right? We look at a small interval around L, say from L minus epsilon to L plus epsilon, right? And there sits L in the middle. Okay. And we would like the values of f to be inside this interval. Right, so let's see, where do we have to look? Right. So basically what we're asking for the graph of f to stay inside this narrow band. Now we see, well, here it's in this band, and there it leaves the band, and then it's in the band, and it leaves the band, and it's in the band, and it leaves the band. Right. But from here onward, right, so from this point onward, f stays inside this narrow band. Right. You can extend the graph more if we like that. And we see, as long as we take x bigger than, say, this value m, say, take x over there, then we'll see that f of x, right, will be in this interval from L minus epsilon to L plus epsilon. Right. So if you take, say, x over here, you see f of x sits in this interval from L minus epsilon to L plus epsilon. Right. So this shows us sort of how to go about writing down the definition for this limit. Right. We must just make x large enough. Right. And then f of x will be as close as we like to L. Okay. So writing that down in formal mathematical symbols looks something like this. So for every epsilon bigger than 0, there is a number m if x is bigger than n, then absolute value f of x minus L is less than epsilon. Right. So this says exactly what our picture here says and what our intuition tells us. Right. We can get f of x as close to L as we like, right, just by taking x large enough. Right. Now, similarly, we can talk about a limit as x goes to minus infinity of g of x. Okay. And if we say this is equal to, say, k, well, the definition looks just the same, right? Except now we want x to be small enough, or put otherwise, a large enough positive, negative number. Right. So, writing that down, for every epsilon bigger than 0, there is, say, an n, so that if x is less than n, then absolute value f of x minus k is less than epsilon. Right. So in this case, our graph will be more or less a mirror image of what we have over there. Right. If we're looking from k minus epsilon to k plus epsilon, right, and we want f of x to be in this band, then we simply have to take x larger than n. Right. In this case, n would be over here. So if we pick x there, then we see f of x will sit over here. Well, g of x would sit over here in this band around k. Right.